Have you ever asked yourself, why do we need model evaluation metrics in linear regression? Well, it's a fundamental question that data scientists grapple with every day. These metrics form the backbone of making accurate predictions and drawing meaningful insights from data. Today, we'll delve into the fascinating world of model evaluation metrics in linear regression. Begin by visualizing a cloud of data points scattered on a graph. Linear regression attempts to draw a line through this cloud, a line that best represents the relationship between these data points. But how do we know if this line is a good fit? That's where model evaluation metrics come in. First up, we have the mean squared error, or MSE. Think of it as the average of the squares of the difference between the actual and predicted values. For instance, if we predict housing prices based on square footage, MSE calculates the difference between the actual and predicted prices, squares it, and then averages these squared differences over all the houses. Lower MSE values indicate a better fit of the model. Next, we have the root mean squared error, or RMS. It's similar to MSE, but we take the square root of the MSE. This brings the errors back to the original units, making them easier to understand. For example, if we're predicting weight based on height, the RMSE would be in the same unit as the weight, making it more intuitive to interpret. Then there's the mean absolute error, or MA. It's the average of the absolute differences between the actual and predicted values. So if we're predicting temperature based on the time of day, MA would calculate the absolute difference between the actual and predicted temperatures and average these absolute differences. It's less sensitive to outliers than MSE or RMSE, which can be a benefit in certain situations. Another metric is the R-squared, or the coefficient of determination. It indicates how well our model explains the variation in our data. For instance, if we're predicting sales based on advertising spend, a high R-squared value would mean that our model explains a large proportion of the variation in sales. Finally, we have the adjusted R-squared. It's similar to R-squared, but it takes into account the number of predictors in the model. So if we're predicting population growth based on multiple factors like birth rate, death rate, and migration, the adjusted R-squared would give us a more accurate measure of how well our model fits the data. In summary, model evaluation metrics in linear regression are crucial for assessing the performance of our models. They offer insights into the accuracy of our predictions and the quality of our models. Mean squared error, root. Mean squared error, mean absolute error R-squared, and adjusted R-squared. Each provide a unique perspective, helping us to understand the strengths and limitations of our models. Remember, no single metric can tell the whole story. It's the interplay of these metrics that paints a comprehensive picture of our model's performance. So the next time you're working with linear regression, keep these metrics in mind. They'll be your guides in the quest for accurate predictions and insightful data analysis.